We start this lecture with an overview, a plan for what will be presented. This pre-lecture is concerned with two topics. We will first discuss the relationship between the real work done by kinetic friction on a deformable body and the calculation that we can perform using the work kinetic energy theorem to determine the change in the mechanical energy due to kinetic friction. We will then determine how to describe a conservative force directly in terms of its potential energy function. We will then use this understanding to develop a description of the equilibrium conditions for objects acted on by conservative forces. Here we see a box sliding down a ramp. We used Newton's second law in Prelecture 6 to determine that the acceleration of the box was proportional to the acceleration due to gravity, with the constant of proportionality being determined by the angle of the ramp and the coefficient of kinetic friction as shown. Since this acceleration is constant, we can apply our kinematics equations we derived for such a motion to determine the speed of the box as it reaches the end of the ramp, if it were released from rest. We can also apply the work kinetic energy theorem here, treating the box as a particle. In this case, the change in the box's mechanical energy is equal to the work done by non-conservative forces. The normal force does no work, since it is perpendicular to the motion. Therefore, we obtain the equation shown that the change in mechanical energy of the box is equal to the integral of the frictional force over the displacement. We can write a form for the friction force in terms of the coefficient of kinetic friction and the normal force. We can use Newton's second law to relate the normal force to the weight. Putting this all together, we obtain an expression for the final velocity as shown. The expression we have obtained from the work kinetic energy theorem is identical to that obtained by using Newton's second law, as it must be. On the next slide, we will discuss the connection between the work done by kinetic friction when we consider the box to be a deformable body and the calculation we can make to correctly determine the change in the mechanical energy of such an object. Here we see a box with an initial velocity v0 skidding across the floor, coming to rest a distance d from its initial position. We can calculate this distance directly using Newton's second law, since the motion is one of constant acceleration equal to minus the product of the coefficient of kinetic friction and g. We can also calculate this distance using the work kinetic energy theorem by setting the change in kinetic energy, minus 1/2 mv0 squared, equal to the macroscopic work done by kinetic friction, minus mu sub k mgd. We've used the words macroscopic work here to indicate that we are interested only in the macroscopic motion of the box. To obtain this motion, we have treated the box as a single object. At the microscopic level, the box does have deformable surfaces, and a calculation of the microscopic work done by friction must account for the interactions at these surfaces. The good news is that we do not need to know anything about these microscopic details to correctly calculate the macroscopic motion of the box. Next time, we will discuss systems of particles and introduce the concept of the center of mass that will justify this claim. Indeed, throughout this course, we will be concerned only with the macroscopic mechanical energy. This energy can be understood solely in terms of Newton's second law. It may be useful at this point to summarize what we have learned so far. We can calculate the work done on an object by a force as it moves through some displacement by integrating the dot product of the force and the displacement. The total macroscopic work done on an object by all forces is equal to the change in the kinetic energy of the object. For conservative forces, such as gravity and springs, we defined a quantity called the change in the potential energy, delta U, as being equal to minus the work done by that conservative force. The potential energy U for an object at a particular location was defined as the change in potential energy of the object between an arbitrary point that defines the zero of potential energy and the specified location. We obtain the potential energy associated with a force by calculating the work done by that force. Can we invert this process? That is, can we start with the potential energy of an object at a particular location and determine the force that is acting on the object at that location? To answer this question, let's consider the one-dimensional case. If we look at the work done by the force as the object moves from x to x plus dx, we see that the potential energy changes by an amount du equal to minus f dx. Consequently, we see that the force acting on the object at a given point is just equal to minus the derivative of the potential energy function at that point. The force is a measure of how fast the potential energy is changing. Of course, this result is not too surprising. If we find the potential energy from the force by evaluating an integral, then it's reasonable that we can find the force by performing the inverse operation, namely by taking the derivative of the potential. Indeed, this result can be generalized to more than one dimension with the use of the gradient operator, but we will only deal with examples that are essentially one-dimensional here. On the next slide, we will verify directly that differentiating the expressions we have derived for the potential energy associated with gravity and the spring force yield the familiar force expressions. We will now consider a simple example to illustrate our result that the force acting on an object at a particular location is related to the spatial derivative of the potential energy of the object at that location. Consider a mass attached to a spring as shown. Defining x to be the displacement of the mass from its equilibrium position, we see that the potential energy function for the mass is a simple parabola as shown. The spatial derivative of the potential energy of the mass at point x is represented on the graph as the slope of the tangent to the curve at point x. The steeper the slope, the bigger the magnitude of the force. Since the derivative of 1/2 x squared is just equal to x, we find that the force is proportional to the displacement from equilibrium, in agreement with our expression for the force law for springs. The same result also applies for the gravitational force. Namely, we know that the potential energy of an object out in space some distance r from the center of the Earth is inversely proportional to r. The slope of the tangent for this 1/r potential as a function of r tells us that the magnitude of the gravitational force is largest at the surface of the Earth and decreases as 1/r squared as we move further away. Since this slope is always positive, the force will always be negative, indicating that the direction of the force always points towards the center of the Earth. This result is just what we expect for Newton's universal law of gravitation. Note that shifting the potential energy function up or down in either example does not change the force, since adding a constant to a function does not change its slope. This result affirms our understanding that we are always free to add a constant to the potential energy function without changing the underlying physics. So far, we have used the word equilibrium to mean the position or orientation where the net force on an object is zero. For conservative forces, we can get an equivalent condition for equilibrium in terms of the potential energy. Namely, since we can express a conservative force in terms of the spatial derivative of its potential energy function, we see that the locations for equilibrium will be at points at which the slope of this potential energy function is zero. For example, here we see the potential energy function for a mass on a spring. The slope of the tangent to this curve is zero at only one point, namely the point at which the potential energy itself is at a minimum. Indeed, the slope of the tangent to any function will be zero at any minima or maxima of the function. Imagine a roller coaster whose track is shown. Since the potential energy due to gravity for an object near the surface of the Earth is just equal to the product of the weight of the object and its height above a position defined to be zero, we see that the height of the track, measured from the zero of potential energy, is directly proportional to the gravitational potential energy of a car at that point. If a car is placed at rest at the minima, B, or either of the two maxima, A and C, it will remain at rest since the net horizontal force on the car at each of these positions is 0. If the car at position B is given a small push in either direction, it will return to the equilibrium position. If the car is given a small push in either direction at positions A or C, however, it will roll down the track, moving further away from the equilibrium position. We say that the equilibrium is stable at the minima and is unstable at the maxima. To generalize this observation, we can say that an object which is initially at rest tends to move towards the configuration where its potential energy is minimized. Note that there is no new physics in this statement. This statement, in terms of potential energy, is absolutely equivalent to the statement that an object accelerates in the direction of the net force acting on it. We conclude with a brief discussion of the main points of this prelecture. First, we investigated the work kinetic energy theorem in the context of a kinetic friction force acting on a deformable object. We found that the work done by such a force cannot be calculated without an understanding of the nature of the interactions at the surfaces. However, the work kinetic energy theorem can still be applied if we consider all forces to act at the center of mass of the object. The integral of the friction force through the full displacement of the object, what we call the macroscopic work done by friction, does determine the change in the mechanical energy of the object. Second, we determined that for conservative forces, the force acting on an object at any point is equal to minus the spatial derivative of the potential energy of the object at that point. Consequently, we can define the equilibrium positions for a particle acted on by conservative forces to be those locations at which the slope of the potential energy function is 0.